Hi again, Professor Huckaba. This is a lecture that we took from last semester, and I repurposed it so that we can use it here. We're starting with Chapter 2, and Chapter 2 deals a lot with, as you might have already read, resonance and how to talk about resonance. So enjoy this lecture, or the start of this lecture. And as always, here is your to-do list. Work on the homework that's due on Friday. Work the Chapter 2 problems if you can, or at least the ones that you can, and finish reading Chapter 2 if you can. And as always, if you're needing help with any assignments or whatever, just email me, and good luck.
A couple of things to think about before class. Chemistry is either really serious or super silly. You can see by the structures of what are called nanoputations. If you've read Gulliver's Travels, you know about the Milliputations, or are they Lilliputians? I get them all confused. They're these small people who imprisoned Gulliver, and somebody had the inspired idea to make some people out of chemistry structures. So these are not just drawings that somebody made. They actually synthesized these molecules that had these structures. Okay, so you could draw them as really these little guys, and the little guys can have a whole variety of jobs, and they even were able to put them on surfaces and make them dance. It was a really cool paper, but chemistry can be really what you make of it, especially organic chemistry, because you can build whatever you want, even little people. No hands. All right, so then let's move on to our discussion, our exploration of resonance. So we left off looking at resonance structures in general and thinking about how electrons move in pi systems and what that means for what the molecules actually look like, right? To kind of go over what you can do with resonance arrows in a pi system, or with double-headed arrows used to denote resonance, there are three basic types of resonance movements. Okay, you can see them up here. There are lone pair to bond, where you're just moving literally a lone pair to where a bond is between two atoms. There is bond to bond movement, that is from one available pi bond to another. In this case, they're showing it through the allyl cation here. And there's another one, the last one, that the most common is a bond to lone pair. It's the opposite of lone pair to bond. You're just taking a bond and giving those electrons to an atom. And using these three, you can do all kinds of things. Here, this is a nitromethane molecule, and you can see the nitro group has one double-bound oxygen and one single-bound oxygen. But using a combination of this lone pair to bond and bond to lone pair arrow movement, you can just flip it. So now you could imagine the molecule really looks like something in between. And the same goes for this N-methyl pyrrolidine or pyrrolidone. Here there's a bond to atom, or bond to lone pair. Yeah, bond to lone pair movement, in addition to a lone pair to bond. Fairly straightforward here. You're going to use these three to construct lots of different movements. Okay, any pi system you can use these three movements on. And it might look like this, where you have kind of complicated looking molecules, but also you can be tested on things that look a lot more simple. Drawing a molecule like this with the two lone pairs, and then asking you to draw some resonance structures is a very reasonable request, right? So if you want to make a resonance structure, maybe you start, I don't know, with a bond to lone pair movement, and you end up with one structure that has a negative charge on the oxygen and a positive charge on the carbon. And again, we use our arrows to show the reverse movement to get back to the original resonance structure. Or you could perhaps have a, I guess this is more of a bond-to-bond movement. So there might be 4. Yeah. Oh, no, there it is, bond-to-bond. That's 3. So if you use that movement instead, what you will get is a structure that looks like this, where you keep the negatively charged oxygen. You have a double bond in the middle, but that positive charge is now on the 4th or the 3rd carbon here. So each of these are reasonable structures. Let's see, give our reverse movement there. Okay. Each of these are reasonable structures, but the question that we're going to try and talk about today is, one, how do you look at a molecule and find out what the resonance structure is? How do you just know? And that's going to be through pattern recognition and knowing some basic rules. And then last, how do you say which structures are better than others? You know, because, you know, whether you draw 6 structures or 20, you have to be able to say which ones matter the most for a molecule and which ones are the ones that we have to consider the most for thinking about what a molecule does in a reaction. So let's first go over some patterns. Because I looked at this molecule and I said, okay, that has this ene-one arrangement. I knew what types of resonance bonds were normal, but that's because I've had a lot of experience, right? I should know how to do that. There are a few easy patterns that we're going to go over that will help you to know for any molecule with conjugation what types of resonance movements you can do. So we'll just call this section patterns. All right, so number 1. We'll do allylic anion. Does anybody remember what an allyl group is? Yeah? No? Nobody. It's been a long weekend. Not a single person. Good. Glad to hear it. An allyl group, if you remember, has a structure of a double bond, 2 double bond carbons with a single bound carbon next to them, and then typically either a positive or negative charge. In this case, I'll do it in a different color. The negative charges are red today. So in this case, this is an allylic anion. An anion means there's a negative charge somewhere, right? Or it is a negatively charged molecule. In this case, this is an allylic anion. Now, just like we did before with the allylic cation, an allylic anion is going to have a resonance that's based around the double bond that is responsible for the negative charge, or sorry, the lone pair that is responsible for the negative charge, and the double bond on the other 2 carbons. Okay, so when we do the resonance movement, lone pair to bond, and then bond to lone pair, then that will give you a structure that looks very similar to the first one here. That is a very weird looking structure. All right. Now, you notice that I used 2 arrows there, and you can use as many as you want during your answers to whatever questions, but it could trip you up. One of the best ways I found to really keep track of all the resonance forms is actually to move 1 arrow at a time. So instead of moving both and showing you that one comes down and the other goes up, you could have like an intermediate structure that you try and think of. Well, I'll just start from this middle structure, and that is to move the electrons over to the other carbon and make a dianion single cation. Okay, so who thinks that the first structure is the worst? Looking at those three, do you have any ideas which one might be the worst structure? Like which, if you were to pick one to be the loser out of this group of three, which would you choose? Would it be number 1? Number 2? I don't know. I see something. Oh, I see some number 3s. Who thinks this is number 3? Hey, all right, good. So this is the type of thing we're trying to find, right? Because each of these we could draw with the rules we just talked about. But if you told somebody an allylic anion looked like this third one, and that's what was the most important structure, you know, they probably wouldn't believe that you were very good at organic chemistry. So you need to be able to say, this structure, you know, don't worry about that one, but the first two, those are the two structures that we should be worried about. Does everybody have the pattern, allylic anion structures? It's just two. It's a pretty simple couple arrows there. All right. What about, where do I put this? Put this here. What about number 2? Number 2 is going to be very similar to what we just looked at. And in fact, one structure that we looked at in a lot more detail last week, and that's the allylic cation. Now, maybe you all remember allylic cations have a structure. Oh, I forgot they're blue. There we go. Positive charges are blue today. Maybe you all remember now the allylic cation, and we talked about the MO theory and how the allylic cation was kind of special because that middle carbon really doesn't have any electron density. And in fact, if we do our resonance movements now, you can see, if we go one at a time, that we really only have the one. Oh, I did it again. They're blue. There we go. They really only have the one arrow that we're worried about. And then we put in the reciprocal arrow there. So this is the allylic cation pattern. So kind of the same deal, whereas the slight difference you might notice is that the allylic anion requires 2 arrows to move the charge over, right? Because you have to worry about the anion actually doing something, whereas the allylic cation more or less just have the single arrow because it's only the bond that moves. Okay, you'll see that more. You'll see this type of difference more as we go through the class. And if you look at the homework, maybe you've already even seen where you need to think about this a little more. All right. Okay. You can have a lot of different combinations, a lot of different functional groups that look like these two already. Okay. Here's the allyl cation we just talked about. You have as well the allyl anion that we drew on the previous piece of paper, but you have lots of things that could have a similar structure. You have this type of ether here. That looks like it could kind of be an allyl anion type of structure, right? Because you have a similar lone pair here and a double bond, and they're both 1, 2. They're ordered in this 1, 2, 3 type configuration, just like this guy, right? So if you're doing a resonance structure for this ether, you could maybe do a similar arrow movement. All right, well, what about something that looks even crazier? What about if you had another molecule we looked at last week? This guy, is that a type of allyl anion? It looks like it to me. Similarly, at the end of class, we talked about amide bonds and how important they were in biology. If you had a form amide, okay, it looks like another allyl pattern, right? So part of the things that we all need to work on is looking at a structure such as the allyl anion here and being able to take the concept and remove the atom labels. Okay, so what I mean by that is being able to look at this and say, it doesn't matter if the structure looks like this. Oh, negative charges are red today. It doesn't matter if the structure, what the structure looks like. You need to be able to see the allyl anion and use a resonance form for whatever it is. Okay. Anions and cations. Oh, there we go. Okay. The next structure, the next pattern that we'll look at is also dealing with cations, except this time it doesn't have a flashy name like allylic, but it does have a nice flashy concept, and that is a lone pair next to a positive charge. And just like how you have a magnet with a north pole and a south pole, a lone pair next to a positive charge will not be happy, and it will want to make or to move that positive charge if possible. So what will happen is something like you have a nitrogen with a lone pair. It's on a carbon that has a, oh no, it's blue. I did it again. A carbon with a cationic charge. Do you remember what that's called? A carbon with a positive charge. It's like carbocation or something like that, right? So you have a nitrogen lone pair next to a carbon cation. What's going to happen? I heard some murmuring. It's not exactly a short answer, is it? The lone pair will move into the bond between the two, and instead of a neutral nitrogen and a positively charged carbon, you will now have a positively charged nitrogen. I almost did it. Positively charged nitrogen and a neutral carbon. Okay? And the reason why this works goes all the way back to that very first class we had together, and that is electronegativity and nitrogen. Because it wasn't so clear in the earlier lectures, but nitrogen is happy to have a positive charge because it is happy to share the electrons with carbon. Carbon is much less happy with a positive next to a lone pair than a nitrogen is to share its lone pair with the next atom. Okay? Now, the fourth one, does everybody have this before I go? It looks like people, yeah.